In 2.6, related rates, our goal is to apply differentiation to real-life problems. If you look at the problems that are coming, these examples, they don't give you an equation and say find the derivative. You have to figure out what is it that they're asking for, what do we have to do with it. Usually with these, pictures can help. So if we're outlining the steps that make this easier, we are going to first draw a diagram. Maybe there is a diagram. In that case, all we have to do is label it. So draw a diagram and or label it if there's already a diagram. Second, we have to figure out what are they asking us to find. Often in these questions, it's going to say find this at the instant when something is happening. So we want to note those things. Note the find, the when, and then there's going to be some given information from the problem, from the words. Then we have to figure out how are we going to put that information together. So we are going to write an equation relating those things that we just wrote down. Find an equation, write an equation that relates, find an equation relating the variables you chose to assign, the constants, things that aren't changing from the previous step. Usually they're going to say, talk about rates. They're going to say find this rate, how fast, how slow, what's the rate at which. They're talking about rates, and rate is derivative. So step 4 is we are going to take the derivative. Now, things are happening mostly in real life as time passes. So we are taking the derivative with respect to time. How fast something happens, miles per hour, feet per second, it's all with respect to time. So that means we're taking the derivative with respect to t, time. Finally, we're going to plug in stuff we know to find what we don't know. Plug in the when and or the given to solve for what we want to find. Let's see how this works. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Let's draw a picture and just make it simple, a simple picture that illustrates this scenario. So I've got a 25-foot ladder sliding down a vertical wall. They're talking about the ground and the distance between the bottom of the ladder and the wall. So let's make our vertical wall against our ground. So here's our wall, our ground. Notice I don't spend too much time making it fancy, just vertical to horizontal. Usually we're going to assume that those are making a right angle, and then a ladder that's leaning against the wall. They said the ladder is 25 feet, and it never talks about the ladder is shrinking or growing. So 25 feet is the ladder, and it will always be 25 feet. If it is a constant length, I mark the length in the picture. Let's see what else we can mark in our picture. The top of the ladder is sliding down the wall at a rate of 3 feet per minute. So the top of the ladder is sliding down the wall at a rate. This length from the top of the ladder to the ground is a length that's changing because the top of the ladder is sliding down. So this vertical length, I need to assign a variable to it because it's not always 25 feet like the ladder or always some amount of feet like the ladder. So if it's a changing length, I'm going to assign it a variable. And usually vertical lengths, I'm going to call y. Horizontal lengths, I'm going to call x. Now, is this length changing? Well, if the top of the ladder is sliding down and the ladder is not changing, the bottom of the ladder will have to be sliding away from the wall. If we read closely, what is the rate of change of the distance between the bottom of the ladder and the wall? Yeah, this length is changing from here to here. So from here, the wall, to the bottom of the ladder, I'm going to call that x. That is also a changing length. Now let's go in here and dissect some more information. The top of the ladder is sliding down the wall at a rate of 3 feet per minute. Whenever I see the word rate, I want to think of derivative because remember, rate is slope, derivative is slope. When I see rate, think derivative. Now the derivative of what? The slope of what? The top of the ladder sliding down the wall. So it's the rate of change of this right here. So 3 feet per minute is dy dt, the rate of change of the length of y. Now, I see another rate later on, the rate of change of the distance between the bottom of the ladder and the wall. Well, again, rate, so again, derivative. This time the derivative, the rate of the distance between the bottom of the ladder and the wall. Bottom of the ladder and the wall. So it's the rate of change of x, or dx dt. Remember, it's all changing with respect to time. Now we have a diagram. Remember our next step, we want to list the find, when, and given. So I'm going to list what I need to find, what moment of time am I finding it, and given what other information. Usually the find we're going to see at the end, the last sentence. It might not always be there, but usually. What is the rate of change of the distance between? So what is that rate of change? So I'm finding dx dt. That's what I don't know. When? Well, I saw the word when. Sometimes they use words like at the instant, when, at the moment, when the top of the ladder is 7 feet from the ground. So the top of the ladder to the ground, that length will be 7. So when y equals 7, given, what other information is there that's given? The ladder's 25 feet, but that's a constant. I already labeled my picture. That derivative I have, the top of the ladder 7 feet from the ground, I have that as my when. Oh, and let's put units. It's not just 7, it's 7 feet. What is the rate of change on the ladder and the wall? So given information looks like there is none. Oh no, there's some given information. We wrote it near the words earlier. We wrote the rate that the ladder sliding down the wall is 3 feet per minute. So that's my dy dt. Now if it's sliding down, it's changing this by making it smaller. So it's a negative 3 feet per minute. Negative 3 because this length is shortening, feet per minute is the units. So I have my find when given. I've labeled things in my picture. Now I need to make an equation that relates the variables. What kind of scenario is this? Right triangle that has sides labeled. The sides are labeled. So if I have a right triangle and it's all about the sides, that's Pythagorean theorem. So now I'm going to go x squared plus y squared, writing the Pythagorean theorem with what I've labeled in the picture, x, y, and 25 squared, using Pythagorean theorem. If it's something changing, I don't put a number. Something changing, I don't put a number. The ladder's length doesn't change, I put a number. Now I take the derivative because I have information about rates. I need to find a rate. So I'm taking the derivative. Now when I take the derivative, I'm taking it with respect to t. Taking the derivative with respect to t, and I have to do it to both sides of my equation. Notice I'm not squaring 25 because it doesn't matter what 25 squared is. When I take the derivative, it's still a constant, it's still 0. On this side, the derivative of x squared is 2x, but I have to use the chain rule because that's a different variable. So I'm going to say with respect to t times dx dt, plus the derivative of y squared is 2y, but times dy dt. I have to use the chain rule there also. Now that I've taken the derivative, I'm going to plug in stuff, my when and my given, to get my find. So Y is 7, so I can take out the y and put 7 in its place. dy dt is negative 3. I can take out the dy dt and put negative 3 in its place. Dx dt, I'm trying to find x. They didn't tell me what x is, so we're going to have to go back to the equation, the Pythagorean theorem that we wrote, and use that x squared plus y squared equals 25 squared to figure out at that instant when y is 7, what is x? Now we can solve this equation, or you memorize your triples. 7, 24, 25. That's a triple. Remember some of the most popular ones? 3, 4, 5. That's a triple. Any multiple of that. 6, 8, 10 is another triple. Lots of triples to help us do these quicker. Knowing 7, 24, 25, I don't have to take too much time solving that. I know x is 24. So I'm going to over here plug in 24 for x. Let's rewrite it with our information plugged in. 2 times 24 times dx dt plus 2 times, oh, I just noticed I left a squared there. Let's fix that. Let's get rid of that little squared. It's 2y, not 2y squared. Excuse me for that mistake. 7, back to plugging it in, negative 3 equals 0. Solve for dx dt. I could have divided out the 2's. That would have made it a little bit faster. Divide out 2. Then I only have to do 24 dx dt minus 21 equals 0, or 24 dx dt equals 21. Divide by 24, and we get dx dt is 7 over 8. Now I need units, so I can think to myself, either dx dt is the change in x, that's the change in feet as we measure the time, which is minutes, or I can look at what's on top. X is measured in feet over time, which is measured in minutes. Feet per minute. Now, words is my question, words will be my answer. So I'm not just going to leave it at 7, 8 feet per minute. I'm going to answer the question properly. I am going to probably just repeat some of these things from there, and I'm going to say, proper answer, when the top of the ladder is 7 feet from the ground, and I'm just looking back to this question to copy that. Instead of what is the rate of change of the distance between the bottom of the ladder and the wall, I'm going to say either the rate of change of the distance between the bottom of the ladder and the wall is, or I can say the bottom of the ladder is sliding away from the wall at a rate of 7/8 feet per minute. Questions are given in words, so answers are given in words. Let's take a look at another one. Air is being pumped into a spherical balloon so that its volume increases at a rate of, keyword right there, how fast, that's another way to say what's the rate. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Let's draw our picture. Now, I don't draw the best pictures, so there's my balloon. We don't need a fancy picture, we just need a simple diagram. Air is being pumped into the balloon, its volume is increasing, so maybe I do something to remember that it's getting bigger. Okay, the volume's increasing. The volume increases at this rate. So volume increases at a rate. Rate is derivative. This is describing volume. So I'm thinking dv dt over here when I see this. How fast? Another rate. This time the radius. How fast is the radius? That's a dr dt. Increasing when the diameter is 50 centimeters. So my picture should probably include something about volume, diameter. If I think of the formula for the volume of a sphere, 4/3 pi r cubed. Radius is in my formula. So I'm going to put radius in my picture instead of the diameter. Now, is the radius always the same amount if my sphere is getting bigger? No. So I'm not going to put 25 here for the radius. I'm going to put R for the radius because it's a changing length. Let's list our find when given. What are we trying to find? How fast, that's a rate, is the radius of the balloon increasing? So my find is dr dt. How fast is the radius, the rate of the radius? When the diameter is 50, well, I could say when d equals 50 centimeters, but if my equation, my picture, doesn't have anything to do with diameter, I'd like to change that to what it does have to do with. So radius is 25 centimeters. Given any other information, yep, dv dt is 100 centimeters cubed per second. It is an increasing scenario, so this is a positive rate. We already have an equation. It was volume, and usually these will be given to you unless they're simple like the Pythagorean theorem. So we already have our V equation. I'm going to write it again over here so that underneath it we can show the derivative. So I'm going to take, at this time, the derivative with respect to t of this side and the derivative with respect to t of this side. Let me write that a little bit better so that we see clearly that we are taking the derivative with respect to t of v and the derivative with respect to t of 4/3 pi r cubed. Okay, from our volume equation, we're taking the derivative. This is just dv dt. Over here, remember 4/3 is just a constant multiple and pi is just a constant multiple, so they hang out while we do the derivative of r cubed. 3r squared, but again it's r, not t, so times dr dt, use the chain rule. We can simplify this a little bit if we want to. For example, the 3's divide out. Then we can plug in our when and given to find what we need to find, dr dt. dv dt is 100, 4 times pi, r, that one instant is 25 squared, dr dt, I don't know. Let's simplify it the best we can, divide by those things, so dr dt will be by itself. It'll be 100 divided by 4 pi and 25 squared. Simplify it so that you see an answer that makes a little bit more sense. So we can take 4 into 100 25 times, then get rid of the 25 with one of those 25s, and without a calculator we can leave a simplified answer as 1 over 25 pi. Now the radius is measured in centimeters, so centimeters per. The time is measured in seconds, so centimeters per second. There's an answer, but remember, when words are the question, words are the answer. So how fast is the radius of the balloon changing? Increasing when the diameter is 50 centimeters. When the diameter is 50 centimeters, the radius is increasing at a rate of 1 over 25 pi centimeters per second, or type it in your calculator and get an answer with a decimal. Either way is good.